Light speed writes a rule most people rarely think to ask about. The night sky above this room, right now, is not showing a single instant. It cannot. Every point of light up there is a separate piece of history, arriving after its own separate delay. And the delays do not match. Sirius, the brightest star in the night sky, sits close enough that its light takes a little over 8 years to reach here. Andromeda, the nearest large galaxy beyond this one, sits far enough that its light takes about 2.5 million years. Look up on a clear night, and both are visible at once, side by side, in the same glance. One carrying news that is 8 years old, the other carrying news older than the human species. The eye looking up has no way to tell the difference. Both simply look like light, arriving now. That is not a limitation of human eyesight. It is the actual structure of the sky. A single, shared now, spread evenly across the stars and waiting to be seen all at once, was not part of the arrangement to begin with. There was this instead. Light, crossing whatever distance it had to cross, at the one speed that does not change, arriving honestly aged. Whether the age is 8 years or 2.5 million, the sky is not a snapshot. It is a patchwork, stitched together because a single pair of eyes standing still on the ground has no way to sort the threads apart. Every telescope ever built, every astronomer who has ever charted a constellation, has been reading exactly this patchwork without needing to call it one. A star catalogue is not a record of things as they are. It is a record of things as their own light happened to leave them, each entry carrying a different, silent asterisk. 8 years old here, 4 here, 2.5 million there. Nobody in the history of astronomy has ever seen the universe as it is at any single instant. Nobody ever will. The instant a person could see does not exist, because the sky refuses to hold still long enough at any one distance to produce one. A star charted tonight may no longer exist in the form its light describes. Nothing about the light itself would announce that change. It simply keeps arriving, faithful to the moment it left, indifferent to whatever has happened at its source since. This is not treated as a scandal by anyone who studies the sky for a living. It is simply understood, quietly, as the price of looking at anything farther away than arm's reach. That patchwork is the plainest possible statement of what tonight is actually about. Light speed is fixed, the same for every observer, no exceptions found in over a century of searching. And because it is fixed, distance becomes a debt that has to be paid in time. A farther star pays a longer debt. Two stars at different distances can never be seen as truly simultaneous, because simultaneous was never a promise the sky was making in the first place. This is not a strange exception carved out for astronomy alone. It is the plainest possible version of a rule that governs every distance, at every scale, all the way down to the room this sky is being watched from. The gap in age between Sirius's light and Andromeda's light is dramatic enough to notice without instruments. The identical gap exists between any 2 points, separated by any distance at all. A lamp across a room, a voice across a hallway, simply too small, at those scales, for anything but the most careful measurement to catch. Something much closer to home makes the identical trade, on a scale small enough to be engineered around on purpose rather than simply observed from a blanket in the dark. A satellite is crossing the sky above this room right now, somewhere among the same stars just described, moving at roughly 14,000 kilometers an hour, carrying an atomic clock sealed inside a shielded metal drum about the size of a small refrigerator. Nothing marks its passage. No sound, no shadow, no reason for anyone below to look up. And yet that clock, at this exact moment, is ticking at a different rate than an identical clock resting on a shelf on the ground beneath it. Not because it slipped out of calibration, and not because the manufacturing was careless. It disagrees with the ground because light's constant speed left the engineers who built it no other choice. The same trade Sirius and Andromeda make with starlight simply compressed from years down to millionths of a second, and corrected for on purpose rather than left to arrive as a patchwork. That is a specification, not an accident. Every satellite in the global positioning system carries a clock deliberately offset from the rate it would keep sitting still on Earth's surface, so that once it is moving in orbit, its ticking lines back up with the ground. Skip that adjustment, and the satellite's clock drifts out of step by about 38 millionths of a second a day. 38 microseconds sounds too small to matter. Light disagrees. It covers roughly 11 kilometers in that span, and GPS times its signals to a fraction of a billionth of a second. Left uncorrected, a position fix would go wrong within about 2 minutes, drifting by something like 10 kilometers a day after that. A phone sending someone down the wrong street, a ship unsure which side of a reef it is passing, a hiker trusting a blue dot on a screen that no longer means what it claims to mean. The system stays honest because, decades ago, someone insisted on taking a strange piece of physics literally. The stakes reach further than a wrong turn. Somewhere tonight, a lineman troubleshooting a fault on a distant part of a power grid is trusting a timestamp that depends on this exact correction being right. Power utilities compare readings across an entire grid using GPS timing, watching for instability before it cascades into a blackout. Aircraft use the same timing to fly approach paths in weather too thick to see a runway. Banks timestamp trades against it, so a dispute over which of two orders came first has an answer sturdier than either party's own clock. None of the people who built these systems had a personal stake in relativity being real. They had a budget, a deadline, and a rule that turned out to be non-negotiable. Ignore how light's constant speed reshapes time, and the tools fail in ways that are immediate and expensive. Believing in the physics was never a requirement. Getting it right was. Here is the piece of physics underneath all of it, stated as plainly as it will ever be stated. Light speed is the one measurement every observer gets identically, no matter how they themselves are moving. Not almost the same, identical. Once that single number is pinned down, something else has to move to make room for it. Clocks, rulers, even the order in which two events appear to happen. Light speed does not sit passively at the edge of what is possible, waiting for something to bump into it. It rewrites how space and time behave, for everyone, all the time, including, quietly, the sky already described above this room, stated as a trade, before any of the mechanism. A clock moving relative to you ticks slower than yours from where you stand. A ruler moving relative to you measures shorter along its direction of travel. From where you stand, two events that look simultaneous to you might not look simultaneous to someone moving differently, and neither of you has made an error. Light's speed stays fixed. Space and time bend instead. Everything that follows is what it costs to keep that trade honest. Why the satellite's clock runs fast at all is worth sitting with, since the number alone explains nothing. Two effects pull in opposite directions. The satellite's motion, about 14,000 kilometers an hour, should slow its clock by roughly 7 microseconds a day. The mechanism behind that is unpacked over the next 2 hours. But the satellite also sits far above Earth in weaker gravity. And weaker gravity lets a clock run fast, by about 45 microseconds a day. 45 gained, 7 lost, 38 net. That is not an approximation chosen to make the arithmetic tidy. It falls directly out of measuring both effects independently and adding them, and it is what the correction hardware built into every GPS satellite exists to cancel, silently, every second the satellite is aloft. Notice what has not happened in that explanation. No gear slipped, no crystal cracked, no signal degraded. The clock behaves exactly as a clock should, and it still disagrees with an identical clock sitting still. That disagreement is not a flaw to root around. It is the entire subject of tonight. Notice how quietly this is all arranged. Nobody had to announce that clocks would disagree tonight over this particular room for this to be true. No alert, no countdown, No visible sign beyond the one already described overhead. A rule about the deepest structure of space and time is being enforced, this instant, by a piece of orbiting hardware doing nothing more dramatic than keeping a phone's map accurate. And that mismatch between how enormous the idea is and how unremarkable its evidence looks is close to the actual shape of everything still to come. A second, quieter correction rides along with the first, worth naming because of what it reveals about how seriously this rule has always been taken. Satellite orbits are not perfect circles. Each one drifts closer to and farther from Earth over the course of a pass, tracing a slightly elongated loop rather than a clean ring, and because gravity's pull on a clock's rate depends on distance, that drift adds a small extra wobble. Enough, at its peak, to shift a position fix by tens of nanoseconds if ignored. Early GPS satellites lacked the onboard computing power to correct for that wobble in flight, so the task fell to the receivers on the ground. A small piece of software riding inside a dashboard unit or a phone in someone's pocket, whose entire job is correcting a clock drift caused by the shape of an orbit hundreds of kilometers overhead. Physicist Neil Ashby's published analyses became the standard reference the GPS program leaned on to get this exactly right. Nobody using GPS tonight has any reason to know that software exists. It runs anyway, in the background of a billion devices, correcting for a piece of geometry almost nobody carrying one has ever heard named. None of what follows is a mystery waiting to be solved. Every claim ahead is drawn from measured records, engineering documentation, published experiments, mission logs, with a named source attached as it arrives. It is a rule already tested more thoroughly than almost anything else in physics, and what is left is simply to watch it operate, case by case, from starlight overhead to a satellite's clock, to a laboratory bench, to the upper atmosphere, to a single human being who has spent more cumulative time above Earth than almost anyone alive. Each case ahead sits at a different speed, a different scale, a different kind of evidence. Starlight, a clock, a particle, a person, a beam of light crossing a garage, and each one answers the same question from a new angle. Given that light's speed cannot move, what has to move instead? Not a bigger mystery accumulating. One answer, approached from enough directions that it stops sounding strange and starts sounding simply true. Held loosely in mind, that is the shape of the whole account. A single refusal, made by light, and everything else in space and time quietly rearranging itself around that one refusal, case after case, at every scale from a star's own age to the width of a hand reaching for a glass of water in the dark. Step back from the satellite for a moment and let the specific hardware fall away. It is one instance of a much larger rule, and the rule is the actual subject of tonight. Every observer, regardless of speed or direction, measures light crossing empty space at the same rate. A person standing still, a person running toward the source, a person moving away at a meaningful fraction of that speed. The same number every time. This does not rest on one clever experiment. It has been tested with steadily increasing precision for more than a century. In one of the more recent tests, two optical cavities rotated continuously against each other in a laboratory found no directional variation in light speed larger than about 1 part in 10 quadrillion. Not very small. A needle searched for at extraordinary resolution and still not found. How that number came to hold its exact value and why light carries no rest mass to slow it down belongs to a different account of this constant's origin. What matters here is narrower and stranger. What happens to everything else once that one measurement refuses to move? A number that large is easy to say and hard to picture. Imagine trying to notice a single extra second added somewhere across more than 30 million years, not measured once, but remeasured continuously over a year of operation, hunting specifically for any hint that light moves faster in one direction than another. It found none. Generation after generation of the same search, growing more sensitive with each new instrument, has returned the identical answer. no direction favored, no observer's motion given a discount. The postulate has not simply survived scrutiny. It has been hunted for exceptions by people whose careers would have been made by finding one, and none have. There is a particular quiet to a result like that. Most of what a night sky offers rewards patience with something new. A fainter star, a subtler color. This measurement rewards patience with an absence, confirmed at ever finer resolution by a community of physicists who would have been thrilled to report the opposite. Nobody builds a career-defining rotating resonator hoping to find nothing. The crack in the rule that would have justified an entirely new theory has simply never been there to find. It is worth admitting, plainly, how strange it is to build an entire career around failing to find something. A physicist spends years designing an instrument capable of catching the smallest imaginable deviation, refines it past what the last generation of physicists could manage, runs it for a year without pause, and the reward, if the instrument works exactly as intended, is silence. No new particle named after them, no anomaly requiring a new theory, just one more decimal place added to a number that already refused to move. That kind of patience is its own quiet form of honesty, and it deserves to be named rather than passed over on the way to the next fact. Speed, at its plainest, is a ratio, distance divided by duration. If the top of that ratio cannot change no matter who is measuring, then distance and duration cannot both stay fixed. One of them, or both, has to give. That is not a poetic flourish. It is the same constraint an accountant recognizes instantly. A fixed total and a fixed line item leave the remaining line items as the only ones free to move. Distance and duration are the line items left free to move. Two observers, traveling differently, can genuinely disagree about how long a clock takes to tick, how long a rod measures, which of two separated events happened first, not through error, and not because something is hidden from one of them, but because those quantities were never the fixed ones to begin with. Light's speed held the fixed position. Everything else was renegotiated to protect it. It is worth sitting quietly with how total that renegotiation turns out to be. Not one clock somewhere, once, under unusual conditions. Every clock, everywhere, all the time, held to a rate that depends on how it happens to be moving relative to whoever is asking. Not one ruler in a laboratory, every ruler, in principle, including the one no one has thought to measure yet. The scale of what is being protected, one number, refusing to move, is matched almost exactly by the scale of what has to bend to protect it. Light speed, then, is not a ceiling bolted onto an otherwise ordinary space and time. It behaves more like a clause in a contract that space and time were always required to honor, and the visible bending, clocks, rulers, the order of events, is what honoring that clause looks like, worked out case by case for the next 2 hours. A ceiling only ever says no. A clause rewrites the terms of everything beneath it, in a specific, calculable direction, every time it is invoked. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. The strangest case comes first. The idea that, at the same time, is not something the universe agrees on by default. It has to be built, observer by observer, out of light signals. And once built that way, two people can watch the same two events and walk away with two different, equally correct answers about which happened first. A plainer version of that idea already governs something. Engineers handle routinely, at ordinary, solar system distances, with nothing hypothetical about it at all. When a spacecraft descends toward Mars, the radio signal confirming each stage. Atmospheric entry, parachute deployment, touchdown, takes somewhere between 10 and 20 minutes to cross back to Earth, depending on where the two planets sit in their orbits. During Curiosity's landing in 2012, engineers at NASA's Jet Propulsion Laboratory watched their screens for confirmation of a descent sequence that itself lasted about 7 minutes, knowing the whole time that the signal reporting each step had already spent longer than that crossing the gap. By the moment the room on Earth learned the descent had even begun, the actual landing, successful or not, had already finished, minutes earlier, on a planet no signal could reach in time to matter. Engineers called the wait the 7 minutes of terror, a name that stuck precisely because it captured how little control anyone in the room actually had, though for that particular landing the true wait ran closer to twice that long. Its outcome already settled before the room even learned it had started. The room itself, that night, was full of people who had spent years of their working lives on a single machine now entirely out of their hands, watching a screen that could only report what had already happened. Some of them had joined the mission as graduate students. Some had grown children by the time the spacecraft finally launched. The cheering, once it came, was cheering for news, not for a live event. No thought experiment is needed to establish that right now, on Mars, and right now, in that control room, were never the same moment in any usable sense. The rover's own computer was built around exactly this fact. Every command it carried out that day had already been written, tested, and uploaded in advance. Because no live conversation with the vehicle was ever going to be physically possible, there is something almost humbling in how completely an entire engineering culture, funded across decades, staffed by some of the most capable people in their field, rearranged itself around a limit nobody in that room could see, touch, or negotiate with. No amount of funding buys back a single minute of that gap. No clever antenna design closes it. The distance between the two planets simply sets the terms, and the only sane response was to stop treating live control as an option and build a machine capable of making its own decisions. During the 7 minutes nobody on Earth could reach it. What follows compresses the same principle down from 10 minutes to a fraction of a second, aboard a single vessel, small enough to expose something Mars, at its own gentler scale, does not. That even with no delay left in receiving the news, two honest observers can still disagree about the order in which the news was made. Picture a scenario, deliberately exaggerated. The real effect at ordinary speeds is far too small for unaided senses to notice. And no spacecraft has ever moved anywhere near this fast. The speed here exists only to make an otherwise invisible effect large enough to see. A slender research vessel, a few hundred meters long, drifts past an orbital relay station at half the speed of light. A single bulb sits at its exact midpoint, between a viewport at the bow and one at the stern. A strip of matte metal paneling runs the corridor's full length, unbroken, except for the bulb housing itself, set flush into the wall like a dark eye waiting to open. At the instant it fires, one pulse of light leaves in each direction at once, racing down the same featureless corridor towards sensors bolted to the hull at either end. An observer aboard the vessel sits beside the bulb, equidistant from both walls, at rest relative to the ship. For that observer, nothing is ambiguous. Light crosses equal distances at an equal, fixed speed, reaching bow and stern at the same instant. One event, no room for disagreement, from where that observer sits. A second witness, stationed on the relay platform, watches the vessel slide past. That observer also measures light speed as the same fixed number in both directions. The rule bends for no one, but the vessel itself is moving toward the bow. At half that speed, follow what that motion does to the two pulses. The stern wall moves forward toward the pulse headed back to meet it, closing the distance faster than either speed alone. The bow wall moves forward too, but away from the pulse headed to meet it, widening the distance still to cross. And so the platform observer watches the backward pulse reach the stern first, the forward pulse reach the bow afterward by a measurable interval. This could be mistaken for a trick of light travel time to the eye, and it is worth ruling that out directly. The platform observer is not simply watching light arrive late to their own eyes. They are measuring, with instruments placed at the bow and stern themselves, the exact moment each flash reaches each wall correcting fully for how long that information then takes to reach the platform. Even after every correction, the two arrivals do not coincide. The stern event happens first. This is not a delay in receiving news. It is a genuine disagreement about when the news was made. The passenger insists, correctly, that both flashes happen together. The platform witness insists, just as correctly, that the stern flash happened first. Neither has erred, and neither would be persuaded by an appeal to the other's instruments, because both sets of instruments already agree with the physics governing their own frame perfectly. Both accounts follow from measuring the identical fixed speed of light from two different states of motion, and both are the accurate record of what occurred in each observer's own frame. Add a third witness, on a platform moving the opposite direction at the same relative speed, and a third true account joins the first two, disagreeing with both, correct in exactly the same way. No fourth platform arbitrates between them. There is no majority vote to settle which account is real. At the same time, turns out to mean nothing until a particular observer's motion has been specified. It was never a fact about the two flashes alone. It was always a fact about the flashes and the observer together. A relationship, not a property, either event, carried on its own. The same lesson the night sky offered quietly, star by star, at the very start of tonight, has just been shown to hold on a vessel small enough to walk the length of in under a minute. The actual size of this disagreement is smaller than the scenario makes it feel, and that smallness matters. Even at half of light speed and across a ship several hundred meters long, the gap between the two flashes, as the platform measures it, comes out to a few hundred billionths of a second, nowhere near what a human eye could register as sequence rather than simultaneity. The effect is completely real and precisely calculable, and at any speed available to ordinary experience. Almost too small to catch directly, making it visible on purpose, with an implausibly fast ship, is one way to show it. Catching it in the wild, arranging nothing, is the harder task still ahead. It would be easy to hear this and assume it belongs to fiction, a device invented for tonight and nowhere else. It does not. The reasoning that just settled the disagreement between passenger and witness is the literal argument physics adopted, worked out from first principles, at the start of the 20th century, and a claim this strange deserves a named source rather than a vague appeal to scientists. The paper is titled, plainly, On the Electrodynamics of Moving Bodies. Albert Einstein sent it to the journal Annalen der Physik on the 30th of June, 1905. It opens not with an experiment or an apparatus, but with a definition. Before anything else can be established, simultaneous needs a working meaning for two clocks that are not sitting next to each other. The answer is a light signal. Send a pulse from one clock to a distant clock and back. Note the round-trip time and declare the two clocks synchronized only if light needed exactly the same time to cross the distance in each direction. That single move defining at the same time through an actual, measurable procedure involving light, rather than assuming everyone already agrees on what it means, is what the vessel and platform scene above was built to dramatize. The illustration is new. The reasoning underneath it belongs to that paper. Once simultaneity is defined this way, it follows directly that two clocks judged, synchronized by an observer at rest relative to them, will not be judged, synchronized by an observer moving relative to them. Not because the second observer's method is inferior, because the definition itself depends on the observer's own motion. Once light speed is held, fixed for everyone, it is worth pausing on how modest this sounds in its own terms. No new particle, no new force, no claim about anything previously unmeasured. A definition, how to decide whether two clocks agree, turned out to carry the entire weight of everything, argued so far, and everything's still ahead, not a new object added to the universe, but an old assumption, hiding in plain sight, that nobody had thought to question until the definition itself was written down carefully enough to expose it. Before the definition of simultaneity even appears, the paper names its own two working assumptions: that physics looks the same to every observer moving at constant velocity, and that light in empty space moves at the same fixed speed for all of them, regardless of the source's motion. Both are framed as postulates, not proofs, starting points to be tested by what follows from them. Every disagreement traced through this account follows from taking those two sentences seriously and refusing to quietly set either one aside once the consequences began to feel strange. The setting the paper came from changes how the achievement should be weighed. Einstein was not working in a university laboratory with graduate students and funding behind him. In 1905, he examined patent applications in Bern for a living, evaluating other people's mechanical inventions to earn a wage, and worked through much of his physics thinking in conversation with a colleague from that same office, Michele Besso, on walks home after their shifts ended. The paper on moving bodies was one of 4 he published that single year, alongside work that helped establish the existence of atoms and the quantum nature of light, a burst still known, a century later, as the miracle year, precisely because so much of it came from someone with no laboratory, no research budget, and no academic title. Its reception was not instant fanfare. It carried no citations to other physicists' work, unusual for a paper of that ambition, and moved through the community slowly enough that a senior physicist named Max von Laue eventually traveled to Bern in person to meet its author, expecting a distinguished professor and finding a young patent examiner still years from an academic post. Max Planck, an editor at Annalen der Physik, recognized the paper's importance early and helped it reach the physicists who would spend the following years working through its consequences. None of that changes a single equation. It does change how the definition of simultaneity ought to be regarded. Not a device invented to make an argument easier to follow, but a claim that survived contact with the most demanding scrutiny available at the time, carried by nothing but the argument itself. It took the wider physics community the better part of a decade to fully absorb what the paper implied, not because the mathematics was obscure, but because giving up a shared, universal now cut against an assumption nobody had previously thought to defend, since nobody had thought it needed defending. Simultaneity had simply always been assumed the way a floor is assumed level without anyone checking. A particular kind of humility lives in that image. A flaw nobody had ever thought to check, because a flaw that has never once given way earns nobody's suspicion. Assumptions built that way do not announce themselves. They simply sit underneath everything else, doing their quiet work, until someone happens to ask the one question nobody thought was a question at all. The real difficulty was the request, buried inside an ordinary-looking definition, to stop assuming something that had never once been tested. Because nobody had realized until then that it was even a claim. None of this settles what happens to cause and effect. If two events can trade places in time depending on who is watching, the immediate worry deserves to be taken seriously rather than waved off. State the worry precisely, because a vague version of it is scarier than the real one. If the stern flash can happen before the bow flash for one observer and the two can swap for another, what stops some observer, somewhere, from watching an effect occur before its own cause? A match flaring before it is struck? A signal received before it was sent? If order itself is negotiable, causality sounds like it should be too. It is not, and the reason is built into the same geometry that made the stern and bow disagreement possible. Look again at what actually swapped order aboard the vessel. The stern flash and the bow flash were never causally connected. Neither made the other happen. Both were caused, independently and at the same instant in the ship's own frame, by the single bulb at the center, radiating outward in opposite directions. Nothing about their order could carry influence from one to the other, because light released toward the stern could never reach the bow before it happened, or the reverse. The order swapped only because nothing needed to travel between the two events to make either of them happen. Now, Imagine two events where one genuinely causes the other. The kind of pair the vessel's own crew would actually rely on. A signal sent from the bow triggers a light on the stern console, dark to lit, carried by a wire down the corridor. That signal cannot cross the ship faster than light, because nothing has ever been shown, in any experiment, to cross empty space faster than light. No observer will ever measure the stern light turning on before the bow switch that triggered it. The order of a cause and its effect is protected because something has to physically travel between them. At a speed with a hard ceiling, every observer measures the same way. This is the actual rule, narrower than the worry that opened it. Two events can trade order between observers only when nothing could possibly have passed between them fast enough to connect them, when neither could be the other's cause. For any pair where one genuinely could cause the other, the order is locked. For every observer, in every measurement made so far, the stern flash and the bow flash never qualified. The bow switch and the stern light always did. That is a real answer, though not yet the mechanism behind it. What specifically enforces that ceiling deserves its full shape once enough evidence has earned it. Rather than being asserted from the start, before that boundary can be drawn properly, the more basic claim underneath needs to be shown as more than a thought experiment. Somewhere, a clock that is not a hypothetical vessel's clock has to be caught disagreeing with another, in a way that was measured, recorded, and published. There is a certain patience required here, and it is worth naming rather than rushing past. A worry this precise, raised and only partly resolved, is not a loose thread left dangling by accident. It is held open on purpose. The way a good question is worth carrying a while before reaching for the answer, long enough to actually feel its weight, rather than having it explained away before it ever had the chance to unsettle anything. In October of 1971, a physicist named Joseph Hafele and an astronomer named Richard Keating boarded a series of scheduled airline flights carrying 4 cesium beam atomic clocks between them. No laboratory, no specialized vehicle. Ordinary airliners, ordinary seats, 4 suitcase-sized clocks strapped in like passengers of their own, each keeping time by counting the oscillations of a cesium atom to a precision no mechanical watch could approach. The plan: fly the clocks eastward around the world, then westward on a separate trip, comparing each set of readings against a reference clock that never left the United States Naval Observatory in Washington. If a moving clock genuinely runs at a different rate than one that stays still, the airborne clocks should return reading a slightly different elapsed time than the one on the ground. A difference small enough to demand atomic precision, large enough, given a jet's actual speed, to be resolvable at all. 2 men and a modest budget. Testing an idea most of physics already believed, but nobody had yet bothered to check outside a laboratory. The logistics were as unglamorous as the physics was exacting. Each clock needed its own dedicated, bolted-down, monitored seat on scheduled flights beside paying passengers, with no idea their trip doubled as a physics experiment. The predicted differences were tiny, tens to a few hundred billionths of a second across roughly 80 hours of flying, small enough that turbulence, engine vibration, or the pressurization cycle of a cabin climbing to altitude could each, on their own, have buried the signal entirely. Cesium clocks were chosen because they do not drift that way. They count something as steady as physics offers, the oscillation frequency of a cesium atom, rather than the swing of a pendulum. Picture the 4 suitcases coming back through customs. Their fragile cargo none of the airline's baggage handlers had any reason to treat carefully, each one still counting the same steady oscillation it had counted since before takeoff. The results matched the prediction with a precision that left little room for coincidence. The eastbound clocks came home having lost about 59 nanoseconds against the ground reference. The westbound clocks came home having gained about 273 nanoseconds. 2 flights, 2 different outcomes, both matching the relativistic calculation worked out in advance. And the fact that East and West produce different results, rather than one simple number, is itself part of what makes this such clean evidence. The asymmetry has a specific, checkable cause, worth naming rather than left as an unexplained wrinkle. Earth itself already rotates eastward, carrying every airport and every stationary clock along with it at roughly 1,600 kilometers an hour near the equator. A jet flying east adds its own speed to that rotation. Relative to the planet's center, one flying west subtracts. Relative to a point not spinning with Earth, the eastbound clocks moved faster than the ground reference. The westbound clocks, in places, moved slower. Slow enough, combined with the added height's own small effect, to run fast rather than slow. Two directions, two outcomes with opposite sign, both accounted for, both matching prediction within experimental error. This closes a door left open by necessity earlier. A satellite's fast-running clock could, in principle, be dismissed as an engineering quirk peculiar to spacecraft, corrected for by trial and error rather than understanding. 4 clocks on commercial airliners, checked against a fixed reference at a naval observatory, remove that objection. 2 men, a set of tickets, and 4 clocks came home reading numbers no ordinary mechanism could explain. Numbers that matched a calculation made from the same rule the satellites obey and the same rule the sky obeys, worked out independently years before GPS existed to need it. The experiment did not stay locked away in 1971. Decades later, a physicist and self-described timekeeping hobbyist named Tom Van Bark drove a second-hand atomic clock up a mountain road in his own family minivan and back down again, chasing the closely related gravitational side of this family of effects, with equipment no more exotic than something purchased, used, and strapped into a passenger seat. Those specific numbers belong to gravity's effect on a clock's rate rather than motion's. A different thread from the one Hafele and Keating pulled. But the fact that a private citizen could meaningfully repeat a landmark government-funded result says something about how far from fragile this physics has become. It tolerates a minivan. Picture the scale of it plainly. 2 atomic clocks riding along on a switchback road at no faster than any commuter's daily drive, quietly recording a difference in elapsed time the driver never felt for a single second of the trip. Nothing about the outing looked remarkable from the outside. Everything about it was. Anyone glancing into that minivan at a stoplight would have seen nothing but 2 boxes of electronics on the passenger seat, with no way to guess that they were quietly rewriting, in real time, exactly how much time had passed since the ignition turned on. Airplane speeds are almost nothing compared to what comes next. A jet crosses the sky at a few hundred meters a second. What follows moves at very nearly the fastest speed permitted at all. And the same effect just measured in billionths of a second is about to decide whether a particle reaches the ground at all. It would be reasonable to assume this effect only becomes measurable once something moves airplane fast or faster. That anything slower simply disappears into noise no instrument could separate from zero. That assumption is wrong. And the way it was shown to be wrong is worth pausing on, because the speed involved is not exotic at all. In 2010, a team at the National Institute of Standards and Technology, working in Boulder, Colorado, physicist Chin-Wen Cho, alongside Till Rosenband, David Hume, and David Wineland, connected 2 optical atomic clocks by about 75 meters of fiber and set one moving relative to the other, not on a jet, not in orbit. At a relative speed of less than 10 meters a second, a brisk walk, a gentle jog, the clocks still disagreed, by an amount too small for any earlier generation of clock to have caught, but well within reach of the optical technology built specifically to look for it. The same laboratory, with the same class of instrument, had already shown the gravitational side of the same physics just as starkly. 2 clocks, separated by about 1 foot in height, ran at measurably different rates, the higher one ticking very slightly faster, exactly as the rule already discussed would predict. There is a particular kind of reassurance in this result that satellites and airliners, for all their precision, could not quite offer. A satellite speed and a jet speed both belong to specialized equipment most people will never personally pilot. A walking pace belongs to everyone. Clocks precise enough to notice a difference at that speed are a genuinely recent achievement. Built one refinement at a time, decade after decade, specifically to chase this rule down to smaller and smaller thresholds. Every time the instruments improved, the rule was there, waiting, exactly where the mathematics said it would be, at speeds too small to have been checkable a generation earlier. The effect governing a satellite's onboard clock, 4 airline clocks, and 2 laboratory clocks connected by 75 meters of fiber, and a person walking past is the identical effect, expressed at wildly different scales. It does not switch on above some threshold speed. It runs continuously, at every speed above 0, too small at ordinary scales for anything but the most sensitive clocks ever built to catch in the act. A body walking across a room, a car idling at a light, a hand reaching for a glass of water on a nightstand, a page turning. Every one of these ordinary motions carries this same effect. Far beneath any clock this room actually owns, happening anyway, exactly as reliably as it happens to a satellite. The difference is never whether the rule applies. It is only whether anything nearby happens to be precise enough to catch it. There is a version of this worth naming honestly rather than glossed over. A body lying perfectly still in this room is not actually at rest in any absolute sense. It is riding along with a planet spinning on its axis, orbiting a star, drifting with that star around the center of a galaxy. Perfect rest, with no speed at all relative to anything, may not exist anywhere for anyone to occupy. Every clock, everywhere, is moving relative to something. The rule has no exit, and no observer has ever needed one. An optical atomic clock of the kind used in that experiment does not simply count faster than its predecessors by a small margin. It compares its own oscillation against a frequency so fast and so stable that a difference of one part in many quadrillion becomes visible over an afternoon rather than a lifetime. Building an instrument that sensitive was not motivated primarily by a desire to catch a walking human's time dilation. It was motivated by timekeeping and navigation needs that demanded ever finer precision for their own reasons. And relativity was simply waiting in the data the moment the equipment became good enough to see it. Roughly 15 kilometers above this room, well past the highest cloud, a proton arriving from deep space, a cosmic ray moving at a significant fraction of light speed, is slamming into the nucleus of a nitrogen or oxygen atom in the upper atmosphere. The collision manufactures new particles on the spot, among them a short-lived one called a pion, which decays almost immediately into something more durable, a muon, a heavier, unstable cousin of the electron, carrying most of the speed of the collision that made it. A muon at rest has a mean lifetime of about 2.2 microseconds before it decays into other particles, a span of time so brief that saying it aloud takes longer than the muon itself typically lasts. Even traveling at very close to light's own speed, a muon with that ordinary, undilated lifespan would cover something on the order of 650 meters before decaying. On average, 15 kilometers of atmosphere stand between where it is born and the ground this room sits on, well above the altitude any passenger jet ever cruises at. By any plain, non-relativistic accounting, essentially none of those particles should survive the trip. And yet muons are, at this moment, the single most common charged particle reaching sea level out of all the cosmic radiation striking Earth. That gap between essentially none should arrive, and they are the dominant particle at the ground, is not a mystery still waiting on an explanation. It was resolved directly, decades ago, by counting muons at different altitudes and comparing to what an undilated lifetime predicts. As early as 1941, well before particle accelerators existed to test the question any other way, physicists Bruno Rossi and David Hall carried detectors to 2 altitudes on Mount Washington in New Hampshire. one near its 6,200-foot summit, one much closer to sea level, and counted arrivals at each. A fixed, undilated lifetime predicts a steep drop-off between the two stations. That is not what the counters recorded. Far more muons survived the descent than the undilated figure allowed, in numbers that matched a stretched, dilated lifetime instead. The mountain itself was chosen deliberately. Tall enough to make the predicted difference visible with the counting equipment of the era, reachable enough by road to staff for a multi-day count. A later, more precise repeat of the comparison, run by physicists Frisch and Smith in 1963, refined the counting further and reached the identical conclusion: far more survivors at the bottom than a fixed 2.2 microsecond lifetime allows, matching instead what the same lifetime predicts once stretched by the muon's own speed, typically close to 99.4% of light speed. At that speed, time dilation lengthens the muon's lifespan as measured from the ground by a factor of roughly 9, turning a 650-meter average range into one closer to 6 kilometers. Still short of 15, but long enough, combined with the natural spread around an average lifetime, to explain why a meaningful fraction reached the ground rather than none at all. The chain that produces the muon is worth walking through slowly and patiently, since each step is ordinary, well-understood particle physics, and the strangeness only enters at the very last step of the story. A cosmic ray proton strikes a nucleus high in the atmosphere and produces a spray of particles, among them charged pions, themselves surviving only tens of nanoseconds before decaying in turn. A pion's decay produces the muon, along with a nearly massless, chargeless particle called a neutrino that carries away energy and is never seen again by any instrument that follows. The muon inherits most of the collision speed, and only at this last step, its own decay into an electron and 2 more neutrinos, does the stopwatch actually start running. Nothing about the collision or the pion required time dilation. Time dilation is only needed to explain how many of the resulting muons survive long enough and far enough to be counted. Counting them required patient instrumentation of its own, and patience is the right word for it. Hours spent watching an empty chamber for a single faint trail, a summit reached by road rather than by convenience. A count repeated enough times to trust the difference between two very similar numbers. Early experiments used Geiger counters and cloud chambers, which make a passing charged particle's path visible as a faint trail of condensation, photographed and counted by hand. Later versions use scintillator panels, slabs of material that flash briefly whenever a charged particle passes through, wired to electronics fast enough to log the exact instant. None of it is exotic by modern standards. Small versions of the same technology are now assembled by university students and hobbyists as an afternoon project, cheap enough that a working muon detector can be built on a kitchen table. A separate, more tightly controlled version of the measurement pushed the test further still, using a machine built and calibrated by hand rather than the open sky. At CERN, in a storage ring built to hold muons on a circular path at 99.94% of light speed, physicists measured the particle's lifetime directly against their lifetime at rest. The muons in that ring lived roughly 29 times longer than an unmoving muon does, agreeing with the relativistic prediction to within about 2 parts in 1,000. A precision available only because a laboratory, unlike the open sky, can set a particle's speed exactly and measure its decay with instruments built for nothing else. A cosmic ray muon's speed is given by nature, uncontrolled, measured after the fact. A storage ring muon's speed is set deliberately, known before a single decay is counted. Two completely different sources of error, converging on the identical prediction, is the kind of agreement a genuine law of nature produces, and coincidence essentially never does. One team looked up at a sky nobody could arrange. The other looked into a ring built and calibrated by hand. Different decades, different countries, different instruments built by people who never had reason to compare notes. and the same number kept arriving from both directions. Unprompted, uncoordinated, simply because it was the number that was actually there to find. None of this required a single unusual assumption about the muon itself, or any special pleading on its behalf. Its rest lifetime is measured independently, in laboratories where it is created and simply left to decay at rest. Its typical speed is measured independently too, from the energy of the collisions that produce it. Time dilation is not a fitting parameter, adjusted after the fact to make a stubborn discrepancy disappear. It is a fixed prediction computed in advance from the same formula already used for a satellite and a set of airline clocks, applied to a completely different object at a completely different speed, landing exactly where the count says it should. This is happening constantly, not as a rare event captured once and filed away. Cosmic ray collisions occur in the upper atmosphere without pause, and a share of the resulting muons are, at this instant, completing journeys through 15 kilometers of air that their own unstretched lifetimes should never have allowed. At sea level, roughly 1 muon crosses every square centimeter of ground every minute, which means, given the surface area of an ordinary human body, several hundred of these particles are passing straight through the person lying in this room right now. Every minute, unfelt, unheard, harmless. Each one a small and completely invisible proof that its own borrowed lifespan is real. None of it can be felt. No warmth, no pressure, no faint tug at the skin. A muon passes through soft tissue the way a thought passes through an empty room, leaving no mark most nights, gone before there was ever a chance to notice its arrival. That absence of sensation is not a gap in the evidence. It is simply the scale at which this rule prefers to operate. Enormous in implication, vanishingly small in anything a body could register directly. A detector left running on a nightstand, the kind students now build for an afternoon's project, would tick along quietly through the dark, registering a small handful of these arrivals before morning, each tick a muon that has just finished proving, once again, that its own borrowed lifespan was real. And every single tick would go entirely unheard by anyone actually asleep in the room. A particle's disagreement with itself, across two states of motion, is one kind of evidence. It is worth asking whether the same effect ever becomes personal, whether it ever accumulates in something with a name, a body, a life story, rather than a laboratory record. His name is Sergei Krikalev, and he has a face, a career, a family that watched him launch 6 separate times, not knowing, each time, exactly when he would come home. Across those 6 missions, he has spent more cumulative time in orbit than almost any other human being. About 803 days. Roughly 2.25 years of a life lived circling Earth at orbital speed, close to 28,000 kilometers an hour. He is remembered, among other things, as the cosmonaut once stranded aboard the Mir space station longer than planned, when the government that launched him dissolved while he was still in orbit, waiting on a ground crew that no longer quite had a country to report back to. None of that history changes the physics of his case. It simply means the number about to follow belongs to an actual, documented human life, not an idealized traveler, invented to make the arithmetic convenient. His speed was nowhere near the muons, and nowhere near the vessel used earlier tonight to make the effect visible on purpose. It was fast enough, held for long enough, to leave a trace that follows the identical rule as everything measured so far. Applying that same relationship to Krikalev's recorded orbital velocity and his 803 cumulative days produces a specific, calculable number. He returned to Earth roughly 0.02 of a second younger than he would have been had he simply stayed on the ground. It is worth being precise about what kind of claim that is, since it differs slightly from everything measured so far tonight. Nobody strapped a personal atomic clock to Krikalev's wrist and read it on landing. The number comes from applying a well-tested formula to his documented speed and documented time aloft. A calculation, not a direct reading. though built from exactly the physics 4 airline clocks and 1 CERN storage ring have already confirmed independently. 0.02 of a second has no weight, no color, nothing to point to, but it has a rough size. And naming it costs only a sentence. A hummingbird's wing completes roughly 1 full stroke, down and back up, in about that span. Not a blink. A blink takes several times longer. Something closer to the single downbeat of a wing too fast for an unaided eye to resolve into anything but a blur. That is the entire scale of what several years spent circling a planet bought, or cost, a man who is, by a margin too small to ever be felt, younger than the version of himself that never left home. Multiply that same margin by the width of an ordinary human lifetime spent entirely at Earth's surface, walking, driving, occasionally flying, and it would still not add up to anything a birthday candle could register. The effect requires genuinely unusual, genuinely sustained speed before the number climbs high enough to be worth naming in 100ths of a second rather than in decimal places with far more zeros. There is something quietly honest about a number this small, and it deserves to be named rather than smoothed over. A different kind of program might reach for a bigger figure to make the case land harder. There is no bigger figure to reach for here, because the actual number, measured against actual recorded flight time, is this small, and reporting it exactly, rather than rounding it up into something more cinematic, is part of what makes it worth believing. The effect is real. It is also, at ordinary human speed sustained for ordinary human durations, genuinely tiny. Both are true at once. None of the 6 missions that produced that total were undertaken with this arithmetic in mind. Krikalev trained for engineering tasks, spacewalks, the operation of 2 different space stations, across a career spanning the end of one country and the beginning of another, entirely reorganized space program. The 0.02 of a second figure was never the point of any of it, simply what the physics quietly attached to a career devoted to something else entirely. The way a shadow attaches to anyone standing in daylight without being the reason they went outside. It is worth pausing on what that means for how this number should be held. Nobody trains for years, says goodbye to family, and straps into a launch vehicle in order to come home a hair's breadth younger. Krikalev did it to do the job in front of him. Repair a station, run an experiment, keep 2 nations' worth of hardware working while the ground beneath him changed governments without asking his permission. The time dilation was never the mission. It was simply true the entire time, riding along uninvited, waiting patiently to be calculated by someone, someday, who thought to ask. Krikalev did not hold the record forever. A decade later, in 2015, fellow cosmonaut Gennady Padalka surpassed his total, eventually logging about 879 cumulative days aloft, a fraction more orbital time, and, by the same arithmetic, a fraction more accumulated time dilation to go with it. The record will likely be broken again by someone else, on a mission not yet flown. What matters is not whose name is currently attached to it. Every additional day spent at orbital speed adds another small, calculable, real increment to a debt that never resets, accumulates identically for everyone who takes on that speed, and always resolves in the same direction. Less elapsed time for the traveller, never more. Krikalev's number, small as it is, invites an obvious objection, and it deserves to be taken seriously rather than waved past. If motion slows a clock, and motion is always relative, Krikalev moving relative to Earth is identical to Earth moving relative to Krikalev. Who is entitled to claim they were the one standing still? From the cosmonaut's own point of view aboard the station, was it not Earth, and everyone on it, doing the moving? Physicists sharpen this worry into something precise enough to actually answer, using a pair of twins rather than a planet and a spacecraft. One twin stays on Earth, the other boards a ship, accelerates away at high speed, travels outward for years, decelerates, turns around, accelerates home, decelerates again to land. When the traveling twin finally steps back out onto the ground, less time has passed for them than for the one who stayed. The same asymmetry Krikolev's small number already demonstrated in miniature. The apparent puzzle. During the outbound and inbound legs, each twin seems equally entitled to say the other was the one in motion, the one whose clock ran slow. Symmetry seems to demand that neither should end up younger. The symmetry is not real, and the reason it fails is the same detail that made Krikolev's own case work. Someone has to turn around. The earthbound twin remains in one unaccelerated state of motion for the entire trip. The traveling twin does not. Leaving, traveling, and returning requires 4 separate departures from constant motion. The stay-at-home twin never experiences even once. Those moments of acceleration are not a minor technicality. They are exactly what breaks the apparent symmetry, and exactly what settles, without ambiguity, which twins account carries less total time. The asymmetry sits entirely in that turning, not in the speed on either side of it. A traveling twin who went faster but never turned around would simply keep drifting away forever, with no reunion and no way to compare ages at all. It is specifically the act of reversing course, breaking from one steady state of motion into another, that hands one twin's account of elapsed time, a privileged claim the other twin's account cannot match. None of this requires a spacecraft to be true. It only requires a spacecraft to make it measurable. 2 people standing in the same room, one of whom later drives across a country and back while the other stays home, have technically run the identical experiment at a scale too small for any wristwatch ever manufactured to register. The reasoning does not change with the vehicle. Only the number does. Neither Krikalev nor Padalka simply drifted away from Earth at constant velocity forever, the way an idealized, symmetry-preserving twin might. Both launched, orbited, curving constantly around the planet, itself a gentle, continuous form of acceleration, never once traveling in a straight line for the length of the mission, and eventually returned and landed. Every cosmonaut who has ever come home and been asked afterward how much younger the mission left them is, by the simple fact of having come home at all, the traveling twin in this exact scenario, the small real number attached to their name simply never blown up to years instead of milliseconds. Constant, unaccelerated motion genuinely has no privileged observer. 2 people drifting apart at a steady speed can each correctly say the other one's clock looks slow, and both are right in their own frame. For as long as the drifting continues, what breaks the tie is not motion itself, but the specific asymmetry of who changed their motion to make the reunion possible. The twin who never turned around is the one whose account of elapsed time, in the end, everyone, including the twin who did turn around, has to agree with. There is a reason this particular puzzle has outlasted a century of newer physics, discovered independently by generations of students who each assumed, briefly, that they had found the flaw nobody else had noticed, still handed from teacher to student the same way it was handed to Einstein's earliest readers. It asks a question anyone can hold in their body. 2 people age at different rates because one of them left. Not a particle, not an abstraction. 2 lives, one slightly shorter than the other by the time they meet again, for a reason that has nothing to do with health or luck, and everything to do with a single acceleration neither could have avoided if the trip was ever going to happen at all. This is not a puzzle physicists have only ever settled on a chalkboard, argued over in principle and never tested in practice. The 4 cesium clocks flown eastward and westward around the world were, in every meaningful sense, a working version of the twins puzzle, run for real. Each airborne clock left a reference clock behind, travelled a closed loop requiring takeoff, turns, and landing. The exact kind of departure from constant motion the twin scenario identifies as decisive, and returned to be compared directly against the twin that never left. The numbers matched, to the nanosecond, what the reasoning predicts for a loop of that shape and speed. The puzzle and its resolution were tested years before this framing of it became a standard way to teach the idea. Everything so far has been about time bending. A clock, a particle, a cosmonaut's own personal calendar, each running at a rate that depends on how fast it moves relative to whoever is watching. Time is only half of the trade struck in the opening minutes of tonight. Space owes the same debt, and it is time to see how it pays it. Return, one more time, to the muon, falling through 15 kilometers of air, surviving a trip its own resting lifetime should never allow. From the ground, the explanation was time. Its internal clock runs slow, stretched by its speed, giving it enough borrowed lifespan to reach the bottom of the atmosphere before it decays. Take the muon's own point of view seriously now, rather than treating it as a convenient fiction invented to make the arithmetic balance. In its own rest frame, the frame in which it is not moving at all and everything else is moving instead, its internal clock is completely ordinary. It lives its normal 2.2 microseconds. No borrowed extension, no exception made on its behalf. If its own lifetime is unremarkable, and it still reaches the ground, something else in its own account of the trip has to have changed instead. What changes, instead, is the distance itself. From the muon's own frame, the atmosphere it crosses is not 15 kilometers thick. It is compressed, along the direction of motion, by the same factor that stretched its lifetime in the ground's account, roughly a 9-fold reduction at the speeds involved. 15 kilometers becomes something closer to 1.5. An ordinary, undulated lifespan is more than sufficient to cross that shortened distance with room to spare. The muon survives its own ordinary countdown because, from where it sits, the trip was never as long as the ground believed it to be. 2 accounts, 2 separate explanations, neither borrowed from the other and neither incomplete on its own terms. The ground watches a stretched clock cross an ordinary distance. The muon, if it could report back, would describe an ordinary clock crossing a shrunken distance. Both predict the identical, measurable outcome, down to the last surviving particle counted at the detector. Time bent for one observer, space bent for the other. They are the same underlying fact, described faithfully from 2 different states of motion. The way the stern flash and the bow flash were the same event pair, described faithfully from 2 different platforms. Picture the muon's own 15 kilometers, compressed to something closer to 1.5 miles, the way a long corridor looks foreshortened from one end when photographed with the right lens. Except nothing here is a trick of photography. The compression is the actual, measured geometry that particle experiences, as real to it as the 15 full kilometers are to the ground station watching it fall. Length contraction is not confined to a muon's private, unreachable point of view, available only to a particle no human will ever ride alongside. At particle colliders such as the Large Hadron Collider, physicists accelerate heavy atomic nuclei, ordinarily close to spherical, to speeds within a whisker of light's own, then smash them together to study the extreme conditions produced. At those energies, the contraction factor reaches into the thousands. A nucleus, normally small and round, the way a marble is round, is compressed along its direction of travel into something closer to a flattened disk, thinner than its own resting diameter by a factor of over 2,000 at the collider's highest energies. A shape no nucleus has ever held while at rest, produced entirely by how fast it happens to be moving when the measurement is taken. The energy density produced when 2 of these flattened nuclei collide depends directly on how compressed they are in that instant, and the models physicists use to interpret the collision are built assuming that contraction is real and precisely quantified. A working engineering input, not a curiosity confined to ships and muons. A clock and a ruler cannot both stay fixed while an observer's motion changes, because holding both fixed at once would force light's own measured speed to change along with them. And that is the one quantity established at the very start of tonight that is not permitted to move. Something has to give. Sometimes the ledger books it as a stretched clock, sometimes as a shortened distance, Which entry appears depends entirely on how the observer happens to be moving, never on which account is somehow more correct. There is a natural temptation to ask which account is the real one, whether the muon's atmosphere is truly shorter or the ground's 15 kilometers is the honest number, and the muon's version merely an artifact of its own strange point of view. The question does not have the kind of answer it seems to be asking for. Neither account is a discount version of the other, waiting to be corrected once the true frame is identified. There is no true frame waiting to be discovered underneath the other two. There is only the invariant they both correctly describe from two different vantage points, and naming that invariant directly, rather than continuing to describe it secondhand, is the piece of the account still owed. Two consistent stories about one single event only make sense, held together if there is a boundary neither one is allowed to cross, keeping the disagreement from spilling into something that would actually break, cause coming after its own effect, a signal received before it was ever sent. That boundary was named once already, as a promise rather than a mechanism. It has earned its full explanation now. One more scenario is worth building, because it puts length, contraction, and the relativity of simultaneity in the same room, and shows they were never two separate strange facts, but two faces of one another. Build it slowly, with the same care given to the vessel earlier tonight. Picture a pole, 20 meters long at rest, and a garage 10 meters deep, with doors at front and back. Ordinarily, the pole obviously cannot fit inside with both doors shut. It is twice the garage's length. Now run the pole toward the open garage at a large enough fraction of light speed that its length, from the garage's point of view, contracts to under 10 meters. For the observer beside the garage, there is a real instant, brief but real, when the entire contracted pole sits inside, and both doors could, in principle, be shut at once before it emerges the far side. The runner carrying the pole sees something else entirely. From the pole's own point of view, it is the garage that moves, and the garage that contracts, shrinking to under 5 meters. Far too small to ever contain a 20-meter pole. Even briefly, the two accounts appear to contradict outright. One observer insists the pole fully fit inside a closed garage. If only for an instant, the other insists it plainly could not have, because the garage, from where the pole sits, was never big enough to try. The relativity of simultaneity, already established, is exactly what keeps both accounts true at once without either being wrong. Both doors closed at the same time is, again, a claim that depends on whose motion is doing the asking. For the garage side observer, front and back door can indeed close simultaneously, for that brief instant. For the pole side observer, those same two closings are not simultaneous at all. The back door closes first, and by the time the front door closes, the pole's own front tip is already out the far side. Neither observer describes an impossible pole, each describes a different, equally valid sequence of door closings, built from the identical rule that broke simultaneity apart aboard the research vessel. Notice what never gets threatened. No matter how the doors and the pole are arranged, no matter which observer is asked, nobody watching, from any position, at any speed, ever measures the pole splintering, or the garage failing to contain a collision that genuinely occurred in every observer's account alike. Physical damage, if the pole and doors ever truly interacted, would be a real, causally connected event. And causally connected events keep the same order for everyone. Simultaneity bends freely for events with no causal link between them. It never bends for the one kind of event every observer needs to agree actually happened. Picture any single event. The bulb firing at the center of the research vessel will do. From that instant, in every direction at once, an expanding boundary spreads outward at exactly light speed. A sphere growing at the one rate every observer measures identically, regardless of their own motion. Nothing that carries influence, energy, or information has ever been shown to get ahead of that boundary. In more than a century of searching, particle accelerators, astronomical observations, laboratory tests, built specifically, deliberately, to look for a single exception. No experiment has ever recorded anything crossing empty space faster than that expanding shell allows. The closest anything has come is worth naming, because nothing has ever exceeded it, is a stronger claim, shown straining against real limits than simply asserted. Inside the Large Hadron Collider, protons are pushed to about 99.99999% of light speed, 9 nines deep, before the digits stop matching, using the full accelerating power of the largest machine ever built for the purpose, and even that much energy cannot close the remaining gap. Nature has done better without a machine at all, without a budget, without a single engineer involved. On the night of October 15, 1991, a detector array in the Utah desert called the Fly's Eye recorded a single cosmic ray proton striking the atmosphere with more kinetic energy than any collider built since has managed to give a single particle. Nicknamed, half-jokingly, the "Oh my God" particle, traveling at very nearly light's own speed, it would have lost a year-long race against a beam of light by a margin measured in thousandths of a hair. Nobody has fully explained what natural process could fling a single proton to that energy. What is not in question is what it did not do. Even the fastest single object ever recorded striking this planet still lost the race. Sit with the size of that loss. A single proton, smaller than anything a human eye could ever hope to resolve, carrying more energy than physicists on Earth can pack into a machine the size of a small city. And still, after crossing unknown distances at unknown speeds for unknown reasons, arriving a fraction of a second behind a beam of ordinary light, whatever violence in the universe produced that particle, it could not buy its way past the one number this entire account keeps returning to. That boundary sorts every other event in existence into two categories. Relative to the bulb's firing, some sit inside the reach of the expanding shell, near enough, late enough, that light or anything slower could have traveled from the bulb to reach them. Those could, in principle, have been caused by the firing, or go on to cause something it responds to. Every observer, regardless of motion, agrees on their order relative to the bulb, because agreeing otherwise would require some influence to have beaten the boundary, and nothing does. Everything else sits outside that reach entirely, too far, too soon, for anything at or below light speed to have crossed the distance in time. Physicists have a name for this second category: events elsewhere, neither in the bulb's past nor its future, connected to it by no possible chain of cause and effect. Most of the universe, at any given instant, sits elsewhere relative to any single event a person might name. It is precisely this category, and only this category, where the order of events becomes negotiable between observers, where a stern flash and a bow flash can trade places without anything breaking, because neither was ever in a position to influence the other, regardless of the order chosen. Sit with how much of existence that elsewhere actually covers. A star flaring on the far side of the galaxy tonight, this instant, is elsewhere relative to this room. No chain of cause and effect links that flare to anything happening here, and will not for tens of thousands of years. The overwhelming majority of the universe, at any given moment, is simply too far away to be connected to this room at all, in either direction, past or future. Causality is not a dense web tying everything to everything. It is a narrow, patient thread, and almost everything that exists sits quietly outside its reach. Causality is not protected by some separate rule bolted onto relativity to patch a hole. It falls directly out of the same boundary that made the vessel's two flashes disagree in the first place. Light speed defines the outer edge of what can possibly be connected to what, for every observer, without exception. And that edge is exactly what keeps a cause from ever landing after its own effect, no matter how the order of unconnected events might otherwise shuffle. It is worth being explicit about what would actually break if that boundary ever failed. Suppose, as a deliberate supposition rather than a measured fact, that some signal could be sent faster than light. A sender aboard a vessel moving relative to Earth transmits it to a receiver on Earth. Because order can already swap between observers for events fast enough to be affected by such a signal, some other observer would measure it arriving before it was sent, have the receiver bounce an equally fast reply back, and the reply could reach the sender before the original message was ever transmitted. A reply to a question not yet asked, arriving in time to change whether the question gets asked at all. Allow even one exception, anywhere, and the neat separation this chapter just drew collapses entirely. The boundary is not policing an aesthetic preference for tidiness. It is the only thing standing between a swap that is harmless and one that would let an effect erase its own cause. Sit with that outcome for a moment rather than rushing past it. A universe where a reply could beat its own question is not simply an inconvenient universe. It is one where the very idea of a story, a sequence of things happening one after another for a reason, stops making reliable sense. Effects would still occur. Whether they occurred before or after their own causes would depend on who happened to be watching. Nothing this account has actually observed behaves that way, not once, in any experiment ever run. The order holds. It has always held. There is a phrase that has been circling since the first minutes over the sky, returning changed each time it reappears. The one measurement nobody disagrees about. It began describing light's raw speed. It now names something larger. The boundary itself, the edge separating what can influence what, is the one structure nobody disagrees about either, even while the clocks and rulers on either side of it keep disagreeing constantly. Light speed is not merely fast. It is the referee running quietly beneath every disagreement tonight has staged, making sure that no matter how differently two observers describe an event's timing or distance, they never once disagree about which of two connected events came first. It is worth answering directly the question this evidence naturally invites. Does any of this amount to time travel? In the specific, narrow sense already demonstrated, yes. Krikalev moved forward in time relative to everyone who stayed on Earth, by a small but genuine, measured margin. A one-way trip into a future slightly ahead of where he would otherwise have landed, achieved by nothing more exotic than speed and duration, exactly as the mathematics predicts for anyone who repeats the trip. It is worth being honest about how modest that permitted direction actually is. Since science fiction imagery tends to promise something grander, nobody is choosing when to arrive, or by how much, the way a dial might be turned. The amount of forward drift is fixed entirely by speed and duration, computed in advance, never adjustable after the fact, never larger than the physics allows for the actual trip taken. What is ruled out completely is the reverse trip, backward, toward a moment that has already happened, because that direction is precisely what the faster-than-light supposition just showed would unravel cause and effect. One direction of time travel is not only permitted, it has already happened, repeatedly, to specific named people, and been measured on their return. The other direction has never been observed, and the same boundary that allows the first is exactly what forbids the second. Long before finance firms started paying by the kilometer for proximity to an exchange, a rear admiral in the United States Navy was already handing strangers a piece of wire to make the identical point. Grace Hopper, a computer scientist who spent much of her later career explaining computing to officials who controlled her budget, grew tired of being asked why satellite communication links felt sluggish, as though sluggishness were a failure of insufficiently motivated engineers. Starting in the late 1960s, she carried a supply of plastic-coated wire, each piece cut to exactly 11.8 inches, and handed one to anyone who asked. That length, she would explain, is the absolute farthest an electrical signal, or a beam of light, can travel in 1 nanosecond, not the farthest a slow signal in a slow country's cables happens to travel. The single hardest ceiling physics permits, for any signal whatsoever, anywhere, the wire reframed an entire engineering discipline. If no signal can outrun 11.8 inches per nanosecond, a computer built from components spread far apart on a large circuit board will always be slower than an equivalent computer, with those same components packed close together for a reason no clever programming can work around. Hopper used the wire to argue, to admirals used to thinking about speed in terms of processor cycles, that the actual limiting factor on how fast a machine could think was ultimately geometry. How far a signal representing one piece of a calculation had to physically travel to reach the next. Decades of computer miniaturization since have been driven, in no small part, by exactly the constraint that piece of navy wire was cut to demonstrate. She kept a second prop in her briefcase, rarely mentioned but just as telling. A coil nearly 1,000 feet long, representing a full microseconds reach, hauled out to make a visual joke at her own explanation's expense, asking her audience how often they were willing to wait a whole microsecond for an answer. Back when a microsecond sounded like nothing at all, the prop worked precisely because it was almost too large to unspool indoors. A microsecond, spent carelessly 1,000 times over inside a slow machine, adds up to real human-scale waiting. A phone that fits in a pocket tonight, outperforming room-sized computers from earlier decades, is not, primarily, a triumph of raw material or clever ideas. It is also a triumph of getting components closer together. So that one boundary, 11.8 inches, a rack of server space, 38 microseconds a day, has less distance left to enforce itself against. There is something almost tender about a rear admiral choosing a piece of wire rather than a diagram or an equation. To make her point, Hopper could have lectured with formulas alone. The number would have been correct either way. She chose instead to put something into a stranger's hand, a length they could coil around a finger, drop in a pocket, carry out of the room, still holding the actual physical scale of the limit they had just been told about. A number stays an abstraction until it becomes a length of wire. Then it becomes something closer to a fact. A hand already knows. The satellites that open tonight are not the only place institutions have quietly restructured themselves around the fact that light speed is a hard ceiling rather than a loose guideline. A very different industry has done the same thing, for a very different reason. And looking at how puts a concrete price tag on how seriously that ceiling gets taken, once real money depends on it. Not a research grant justified once to a funding committee, but an ongoing, competitive, repeated bet placed daily by people with no professional interest in relativity whatsoever, who simply cannot afford to be wrong about it. Financial exchanges match, buy, and sell orders inside computers housed in specific, unremarkable-looking buildings. A data center outside Chicago for one major futures exchange. A particular building in New Jersey for a major stock exchange. Warehouses that from the outside give no hint of what happens to travel time inside their walls. A trading firm's server sitting even a few kilometers farther from that building than a competitor's is not at a small disadvantage. It is at a fixed, physically unavoidable one. Light moves a little slower through fiber optic glass than through open space. A detail not unpacked here. But even accounting for that, every additional kilometer of cable adds a measurable handful of extra millionths of a second before an order can arrive. Roughly 5 microseconds per kilometer. One way, not enough time for a human being to notice anything. More than enough for an automated trading system, competing against others in the same narrow window, to lose a trade specifically because its server sat farther from the exchange. The response was never to try to beat light's speed. Nobody can, and every engineer in this industry knows it going in. The response was to get physically closer, as close as engineering allows. Firms now pay exchanges directly for the privilege of installing their own servers inside the very same data center as the exchange's matching computers. Co-location, with published monthly rents running into 5 figures at some exchanges purely for a rack of server space measured in feet, rather than kilometers from the machine actually executing trades. When fiber optic cable itself was judged too slow, firms went further, building dedicated microwave relay towers in a line between Chicago and New York because a signal traveling through open air moves closer to light's true vacuum speed than the same signal crawling through glass. None of this is theoretical caution. It is money, spent by people with every incentive to find a shortcut around light speed if one existed, and none of them has found one. Navy admirals learning why a satellite call felt sluggish, GPS engineers writing correction software into a receiver's firmware, a trading firm signing a lease measured in server rack inches. None of them met each other. None of them needed to. The physics did the coordinating on its own. That last detail is worth letting sit for a moment. A physicist in a laboratory, a network engineer in a data center, a Navy admiral holding a piece of wire, a trader watching a screen in Chicago. None of them compared notes, none of them shared a field, and all of them arrived at the identical respect for the identical number, purely because reality kept charging the identical price for ignoring it. A rule does not need believers to be enforced. It only needs consequences, applied consistently enough, for long enough, that eventually everyone paying attention arrives at the same answer independently. A claim this absolute invites a genuine counterexample, and it deserves to be met honestly rather than talked around. Astronomers routinely describe galaxies receding from this one at sufficient distance, faster than light. A sentence that sounds like exactly the violation just ruled out. It is not, and the reason sharpens the rule rather than breaking it. The speed limit defended so far, from the vessel to the muon to the proton in Utah, belongs to motion through space. An object, a signal, a particle, crossing the distance between 2 points that both sit still relative to some larger frame. What is expanding, at the largest scales the universe offers, is not an object moving through space at all. It is space itself, growing between galaxies that are, for the most part, barely moving relative to their own immediate surroundings. Beyond a distance of roughly 13 to 15 billion light-years, a threshold astronomers call the Hubble distance, enough new space continuously appears between here and a given galaxy that the total distance grows faster than light could cross it, even though no galaxy out there is breaking any local speed limit where it actually sits. Ask any observer on any one of those distant galaxies to measure their own local motion relative to their own immediate surroundings, and the number they get back will be small and ordinary, well inside every limit already established tonight. Two swimmers standing still on two different rafts, with the river between the rafts itself widening, can end up farther apart faster than either could ever swim, without either having moved through the water at all. There is a quiet strangeness worth pausing on here. The universe is, in a very real sense, retreating from itself in every direction, and no single point within it is doing anything unusual to cause that retreat. Stand anywhere this room, a ship 1,000 light-years off, a galaxy near the edge of what can ever be seen, and the same pattern holds. Everything sufficiently distant recedes, and nothing sufficiently distant needs to move to do it. It is one of the few genuinely humbling facts a person can hold at once. Nothing in this room is expanding, and yet everything far enough away is getting farther, simply because the space connecting here to there keeps quietly growing, with no observer anywhere required to notice. This is not a loophole carved out to save the rule from an inconvenient exception. It is a distinction the rule always contained. Light speed constrains how fast anything can move through space, locally, in the immediate neighborhood of any single observer. It says nothing about how fast space itself is permitted to grow between two neighborhoods far enough apart. Every measurement so far, the satellite, the airline clocks, the muon, Krikalev, the twins, the nuclei, flattened at the collider, took place within one local patch of space, where the constraint applies without exception and has never once been observed to bend. The galaxies receding faster than light are not counterexamples to that constraint. They are a reminder that it was always more specific and more interesting than nothing goes fast. It is worth noticing too that even this exception opens no practical shortcut. A galaxy receding beyond the Hubble distance cannot signal this room any faster because of that recession. If anything, its light has a harder time reaching here at all, since the space between there and here keeps growing while the signal still crosses it. No message rides that expansion to arrive early. No cause reaches an effect ahead of schedule because of it. The exception changes how astronomers describe distance at the largest scales. It changes nothing about what any observer, anywhere, can actually do with that distance. One more apparent exception is worth admitting into evidence, because it fooled trained astronomers before it was properly understood. Since the 1970s, radio astronomers observing certain distant quasars, extraordinarily bright cores of galaxies, powered by supermassive black holes, the same kind of distant object whose light has been aging quietly in transit this entire night, have recorded blobs of material within their jets, appearing to cross the sky at several times light's own speed. Quasars named 3C273 and 3C279 were among the first documented cases, tracked using networks of radio telescopes spread across entire continents, precise enough to measure a jet's motion month by month. Nothing in those jets is actually outrunning light. The illusion is built from a specific, almost architectural coincidence of geometry and timing. The material is genuinely moving very fast, close to light's own speed. And, in the cases where the illusion appears, happens to be moving almost directly toward Earth, along a line only a few degrees off an observer's line of sight. Picture a single glowing knot of material torn loose from the black hole's surroundings and hurled outward along the jet, moving almost exactly toward this planet. It emits light at one position, then, a short time later, emits more from a position much closer to Earth, having nearly kept pace with its own first signal in the interval between the two emissions. The second burst has a much shorter distance left to travel, arriving far sooner after the first than the true elapsed time between the emissions would suggest, compressing, in the recorded timeline, an interval that took much longer to actually happen. Divide the blob's real sideways distance by that artificially compressed apparent time, and the resulting speed comes out faster than light. Not because anything moved that fast, but because the clock being used, the arrival time of the light itself, was distorted by the jet's own near light speed approach. Astronomers do not treat these measurements as evidence against relativity. They treat them as confirmation of it. The specific pattern of apparent speed, brightness, and direction produced by a jet at that speed and angle matches in exquisite detail what the theory predicts. The illusion is not a loophole, it is a fingerprint, one relativity itself predicted before astronomers ever caught it in the act. There is something satisfying in a theory that predicts its own future confusion. Long before any telescope recorded a jet appearing to outrun light, the mathematics already contained the exact conditions under which such an illusion would appear, and the exact numbers it would produce. When astronomers finally saw it, they were not stumbling onto a mystery. They were checking an answer that had been waiting, quietly, for someone to build an instrument capable of asking the question. 3 apparent exceptions have now been examined in a row. The vessel's swapped flashes, a galaxy's expanding distance, a quasar's approaching jet, and all 3 resolve the same way. Not by breaking the ceiling just defended, but by revealing something about how an observer's own position and motion shape what gets measured, layered on top of a ceiling that never moved. A skeptic would be right to ask whether that repetition is simply what happens when a rule is vague enough to explain anything after the fact. Whether it's a geometry effect. Is a phrase flexible enough to be reached for no matter what the observation turns out to be? It is not, in these 3 cases, because the geometry each time made specific, falsifiable predictions before the fact. not flexible excuses after it. The relativity of simultaneity was worked out from the light signal definition years before anyone measured a jet's apparent motion. The Hubble distance threshold follows a specific formula, not a hand wave, and gets the wrong answer immediately with the wrong distance or expansion rate. A jet's apparent speed, computed from the actual angle and velocity involved, has to land on the actual number observed. Every one of these predictions could have failed to match its observation. None of them did. In September of 1908, a mathematician named Hermann Minkowski stood before an assembly of scientists in Cologne and opened his address with a sentence still quoted. More than a century later, whenever this exact question comes up, henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. He was reporting a mathematical result delivered with an urgency that, in hindsight, carries its own quiet weight. The Cologne address turned out to be Minkowski's last public lecture. He died the following January, leaving other physicists to carry the framework he had just unveiled the rest of the way. The relationship between the man delivering it and the theory it grew from carries its own small, human irony besides. Minkowski had been Einstein's own mathematics professor years earlier at the Zurich Polytechnic, where by his own later account the young Einstein skipped lectures often enough that his teacher considered him something less than a promising student. When Einstein's paper on moving bodies eventually reached him, Minkowski did not simply admire it from a distance. He spent several years reworking its physics into a new mathematical language, built specifically to make space and time's entanglement visible rather than merely implied by a set of equations. Einstein's own first reaction was not gratitude. He is reported to have dismissed the reworking, at least initially, as unnecessary mathematical machinery layered onto a physical idea that did not need it. He changed his mind within a few years, once he found himself needing exactly that machinery to extend the theory further, into gravity itself. The student's idea and the skeptical teacher's mathematics ended up inseparable, neither finished without the other. A professor who once doubted his pupil's mathematics, and a pupil who once doubted his professor's elaboration, each turning out to need the other's contribution before either piece of physics could stand on its own. The mathematical result is worth walking through once, slowly, in plain language, because it is not difficult stated carefully, only unfamiliar. Take any two events, the bulb firing and light reaching the bow wall, say, and measure the distance between them and the time between them, the ordinary way, with a ruler and a clock. Different observers, moving differently, get different numbers for that distance and different numbers for that time. But combine those two numbers in one specific way. Square the distance, square the time multiplied by light speed, and subtract one from the other. And something remarkable happens. Every observer, no matter how they are moving, computes the identical combined value. Physicists call it the interval between the two events. It is not distance. It is not duration. It is the one quantity built from both that refuses to change. The way light's raw speed itself refused to change in the opening minutes of tonight. Distance and duration are what a single observer sees when slicing that combined interval apart along their own particular direction of motion. Different observers, slicing at different angles, get different looking distances and durations from the identical, unchanging whole. Nothing about the underlying interval changes when this happens. Only the angle of the cut does, and the two numbers that fall out of it. This is the deepest pattern the whole account has been circling since the very first glance up at the sky. Distance and duration were never actually two separate, independent facts about the universe, each trustworthy on its own. They were always two projections of one combined structure, space-time, sliced apart differently depending on how an observer happens to be moving. The way a single solid object throws a different shaped shadow depending on the angle of the light falling on it. A clock ticking slow and a ruler measuring short are not two unrelated inconveniences. They are the same underlying invariant. The interval, read off along different axes by observers not standing still relative to each other. Light speed is what makes the combination work. It is the specific conversion rate needed to weave a distance and a duration into one quantity that stays fixed. The exchange rate, if that word helps, between how far something is and how long it took, fixed once and for all, so that whatever else bends, the interval between two connected events does not. Light speed changes the rules of space and time because it is the constant that space and time both have to bend around, in order to protect something deeper than either of them measured alone. This is not merely an elegant way to re-describe everything already covered. Look back at the sky one more time, and the same mathematics is already there. Unlabeled, Sirius's 8-year-old light and Andromeda's 2.5 million-year-old light are each a faithful interval, sliced by the same fixed distance between here and there, offering up whatever duration that distance happens to demand. It is the working assumption underneath the very first case tonight opened with. The engineers who program a GPS satellite's correction are not, in any meaningful sense, treating space and time as two separate, independently trustworthy quantities that happen to need patching. They are, whether the documentation uses this exact language or not, tracking one interval, sliced differently by a clock on the ground and a clock in orbit, and correcting for the difference in how each slice comes out. The mathematics Minkowski handed a physics community still adjusting to Einstein's paper turned out, decades later, to be the exact mathematics an entirely different kind of engineer would need for a technology neither man lived to see. It is worth admitting plainly that this is the point where the picture stops being fully paintable in the mind's eye, the way a satellite or a research vessel can be. Nobody has ever seen a space-time interval the way a muon shower or a flown atomic clock can, in principle, be seen or read directly. It is a mathematical quantity, arrived at by combining two other quantities in a specific way, and trusting it means trusting the mathematics that produces it. Mathematics that has, in every single case walked through tonight, produced the identical prediction that the actual clocks, the actual particles, and the actual cosmonaut then went on to confirm. That is not a small thing to accept without seeing it directly. It is also not, strictly, faith. It is the same kind of trust already extended, earlier, to a satellite correction nobody in this room personally verified, and a muon count nobody in this room personally ran. The interval asks for nothing more than that same trust, applied one level deeper. There is a phrase that opened this account, describing a number, then widened to describe a boundary. It closes now describing this: the interval between two events, the one distance nobody disagrees about. However differently, observers describe the space and the time that separately make it up. None of this required abandoning the two flashes aboard the research vessel, or the 4 clocks on the airliners, or the muon crossing 15 kilometers of sky, or the 200ths of a second a cosmonaut gave up to orbital speed. Each of those was already a faithful reading of the interval, taken from one particular angle. The mathematics simply revealed that all of those readings were describing one structure the entire time. Quietly, underneath every disagreement walked through tonight, there is a certain rest in arriving here. Not the rest of a mystery solved, since nothing tonight was ever presented as unsolved. Every claim carried its source, every number its citation. The rest of a shape finally seen whole after being handed piece by piece. A satellite's correction, a vessel's 2 flashes, a mountain's muon count, a cosmonaut's small debt, a pole that fits and does not fit depending only on who is asked. None of those pieces needed the others to be true. Together, they simply stop looking like a list and start looking like a single object, examined patiently enough from enough angles to finally be recognized. None of what filled the last 2 hours needs to be carried consciously for it to keep working. Return, one last time, to where tonight began. A satellite, somewhere above this ceiling, crossing the dark at 14,000 kilometers an hour, its onboard clock deliberately mistuned so that once in motion, it agrees again with the ground. It is up there now. It does not pause for the room to notice it. It does not require belief to keep correcting itself by millionths of a second, over and over, so that a phone somewhere can find a street corner correctly. Somewhere in the air, above that same ceiling, a muon born from a cosmic collision a few kilometers up is completing a fall its own resting body should never have survived, carried the rest of the way by a stretched clock or a shortened sky, depending only on which observer is asked. It will decay soon, unnoticed, and another will already be falling in its place. Several hundred more are passing through this room in the time it takes to read this sentence. Through the walls, through the ceiling, through whoever is listening, leaving nothing behind to show they were ever here. And somewhere in the historical record, a specific man who once circled this planet for a total of about 803 days, remains younger by roughly the length of one hummingbird's wing beat than the version of himself that would have stayed on the ground. A debt too small to ever be felt, paid in full, and never taken back. None of these things are happening because tonight described them. They were already happening before this room existed, and they will go on happening after it is asleep. Light speed holds its place, refusing to move for anyone, and everything else. The clocks, the distances, the order in which unconnected things occur, quietly rearranges itself around that one refusal, the way it always has, the way it will keep doing long after this particular account of it has ended. There is a stillness worth allowing here before the account closes. Nothing that has been described tonight requires effort to keep happening. No one has to remember the interval, or picture the muon, or hold the cosmonaut's small debt in mind for any of it to remain true through the night. The rule asks nothing of the room it operates in. It simply operates the way it operated for every night before this one. Back through the Bern patent office, and the airliners and the mountain in New Hampshire. Back before any of those people existed to notice it, and the way it will keep operating for every night that follows this one, whether or not anyone is awake to be reminded. Return, once more, to the sky that opened this account. Sirius 8 years old, Andromeda 2.5 million, both arriving in the same glance, neither one lying about its own age. What looked at the start like a simple patchwork, stitched together only because a pair of eyes on the ground has no way to sort the threads apart, has a deeper name now. Each point of light is carrying its own interval intact across whatever distance separates it from this room. The one quantity, distance, and duration woven together, that light's fixed speed never once allowed to go dishonest. The sky was never one moment. It was always this instead. Countless separate, faithful readings of the same underlying invariant, arriving one patient photon at a time. There is nothing left to solve tonight. The rule was never hiding. It was only waiting to be looked at closely enough to notice that it had been running the entire time. Overhead, underfoot, in a sky that was never one single moment to begin with. And, in the smallest possible measure, inside the body of at least one person who once left the ground and came back, very slightly changed. The universe will still be here when you wake up. So will we. Good night.